In this video, we will talk about the Taylor series, which we've discussed a little before, and we will also introduce the Laurent series. This is our overview slide, which we'll spend about 5 minutes going over before we go through each topic in more detail and with more examples. We will start by talking about convergence, and we'll start with convergence of real series. And so this is something you have seen from your first year calculus course, but we're going to do a quick review. So first we say that an infinite summation of real numbers x of n is said to converge to the value of capital S if S is equal to the sum of n equals 0 to infinity x of n approaches a finite real number. Absolute convergence means that a series is said to converge absolutely if the sum of the absolute values of all the x of n approaches a finite real number. And then we can use a ratio test to establish absolute convergence for a series. If the terms of an infinite series satisfy this ratio test here, that the limit as n approaches infinity of x of n plus 1 over x of n is less than 1, then the series converges absolutely. There are other tests for convergence other than the ratio test, but this is the one that we will be using in this book and will be sufficient for this book. We'll continue talking about convergence, but we'll consider a complex series. So an infinite summation of complex numbers Zn is said to converge to the complex value capital S if S is equal to the sum from n equals 0 to infinity Z sub n approaches a finite complex numbers. And for convergence of an infinite complex series, both the real and imaginary parts must converge. So if Zn is equal to xn plus I yn and Sn, the number that it's converging to, is equal to S sub R being real, plus S sub I being the imaginary part, then S sub R, the real part, must approach a finite real number, and S sub I, the imaginary part, must also approach a finite real number. And then we say that a complex series converges absolutely if the Z sub n, the absolute value of Z sub n, approach a finite complex number. And we also have the ratio test. It's totally analogous. So the limit of n approaches infinity, Zn plus 1 over Zn is less than 1, absolute value less than 1, then the series will converge absolutely. Finally, we'll start talking about Taylor and Laurent series. We'll review Taylor series expansion given by this formula here with the C sub I. Where is C sub I given? Oh, right here. C sub n is given by this formula here. And we have this ratio test to see if the Taylor series converges. And we'll introduce the Laurent series expansion with this formula here. However, I will note that we are not given in this chapter the formula for the C sub n of the Laurent series. So we don't know yet how to calculate the C sub n when n is negative. But we'll do that in probably the next chapter or two. And we'll introduce the Laurent series, we'll talk about its convergence. So that's our review. So let's start now in our topics by looking at convergence of a real series. So first we start with the definition of convergence. So an infinite summation of real numbers x of n, that's a series. So a summation is a series of x of n, is said to converge to the value of S if S equals the summation n equals 0 to infinity x of n approaches a finite real number. And then we say we have absolute convergence if a series is said to converge absolutely if the sum from n equals 0 to infinity of the absolute value of x of n is a finite real number. So you can see that absolute convergence is a stricter thing than just regular convergence, because regular convergence, you can have some negative numbers offsetting some positive numbers, but here in absolute convergence, you don't have that. So it's a stricter type of convergence. And if a series converges absolutely, it will always converge. And again, absolute convergence is a more rigid requirement than convergence. And even if a series does not converge absolutely, it still may converge. We have this ratio test to establish absolute convergence of a series. So if the terms of an infinite series satisfy this test here, that the limit as n approaches infinity of the absolute value of x of n plus 1 over x of n is less than 1, then the series converges absolutely. And there are other tests for convergence other than this ratio test, but the ratio test is the only one we will be needing for this book. I have these 3 examples to determine if these three series converge or diverge. And this will look a lot like what we did in first year calculus. So maybe this will be nostalgic for you. And for all 3, we're going to use the ratio test because I haven't given you, or the book hasn't given you any other way to prove convergence. So we will consider the limit as n approaches infinity of x of n plus 1 over x of n. So here I have the limit as n approaches infinity, and for a, part A, I plugged in n plus 1 for n. So I have 2 to the n plus 1 over n plus 1 factorial, and then we divide by x of n. So all I did is I multiplied by the reciprocal, so I have n factorial over 2n. From there, it's algebra. 2 raised to the n plus 1 is 2 times 2 to the n plus 1 factorial is n plus 1 times n factorial, and now you can see I have my n factorials canceling out my, this should be 2 to the n, not 2n. So now I can cancel out my 2n's, and I'm left with the limit as n approaches infinity of my 2 on top and n plus 1 on bottom. As n approaches infinity, the denominator will grow really fast. 2 just stays constant. So we're going to approach 0. And since 0 is less than 1, the absolute value, I should have put absolute values on everything, which I forgot. So the limit, I should put absolute values on all of this. Well, it's equal to 0. So since it's less than 1, we can say that the series converges absolutely. For my next example, I'm going to plug in x of n plus 1. So over here in example B, I have n plus 1 squared. I have 2n plus 1 plus 1, so that's 2 raised to the n plus 2 over 3 to the n plus 1. And then I divide, so I'm just going to multiply by the reciprocal here, my 3n over n squared 2n plus 1. Now again, some algebra. My 3n here cancels with this, so I'm left with the 3 on bottom. My n squared is going to cancel, actually it doesn't cancel, but my 2n plus 1 will cancel with all but one of the 2. So what I'm left with is my n plus 1 squared. I'm left with a factor of 2, and on bottom I'm left with n squared and a factor of 3. So all of those are over here. Now I moved my 2 and 3 in front. I multiplied my n plus 1 squared out, and then I have my n squared. If you remember from first year calculus, when you have a polynomial over a polynomial and you're looking for the limit as n approaches infinity, you only need to look at the highest power and take the ratio. So this is 2n squared over 3n squared, so the ratio of the highest polynomials give you 2/3. So since 2/3 is less than 1, I didn't explain that really, really well, but hopefully you'll kind of remember that. So, right, if this were less than, I should explain, I feel obligated now. So if this was n squared over n, then the n squared would dominate and you'd go to infinity. If it was n over n squared, then the n squared on bottom would dominate and you'd go to 0. But since the highest degree is equal, you just take the ratio of their coefficients. So the coefficients is 2/3. 2/3 is definitely less than 1. So this series here converges absolutely. Okay, and our last example here. So I have the limit as n approaches infinity. I plug in n plus 1 raised to the n plus 1. That looks kind of strange. N plus 1 factorial, and I multiply by the reciprocal of this, n factorial over n raised to the n. Okay, so now to simplify algebraically, my n plus 1 factorial is equal to n plus 1 times n factorial. So my n factorials cancel out. Let's see, there's not much I can do with this right now. Oh, but I do have n plus 1 on bottom, so that can cancel out with one of these n plus 1s on top. So what I'm left with is n plus 1 raised to the n over n raised to the n. So I can now, I can work with this now a little because they're both on the same exponent. So that's equal to 1 plus 1 over n raised to the n. And that's equal to e. If you don't know that, you can still see that this is going to be something greater than 1, which means this is our example of a series that diverges. So that's convergence of a real series. So now we can talk about convergence of a complex series, which is very similar to convergence of a real series. But for a complex series, again, we define convergence. So an infinite summation of complex numbers Zn is said to converge to the complex value of capital S if S is equal to the sum from n equals 0 to infinity Zn approaches a finite complex number. And for convergence of an infinite complex series, the real and imaginary parts must converge. So you can analyze the real and imaginary parts separately, but we also have, the idea of absolute convergence, and then we have the same ratio test to test if a complex series diverges or converges. And so we'll use this ratio test. And I have two examples for you here. The first one is the series n equals 0 to infinity, 1 plus I to the n over 2 raised to the n plus 1. And the second example is n equals 0 to infinity, n factorial squared, 3 minus I raised to the 2n, all over 2n factorial. This one looks kind of complicated. We'll do the easy one first. So the limit as n approaches infinity of z to the n plus 1 over z to the n with the absolute value around it is equal to the limit as n approaches infinity. So I'm going to, for part A, I'm going to substitute n plus 1. So we have 1 plus I raised to the n plus 1 over 2, and then n plus 1 is going to give me n plus 2. And then I multiply by the reciprocal of what's here to get z over n, right on the bottom. So I'm going to have 2 raised to the n plus 1 over 1 plus I raised to the n. Now we do some algebra. So here my I plus 1 to the n is going to cancel with all but one factor. And then here my 2 to the n plus 1 will cancel with all but one factor. So I'm going to get the absolute value of I plus 1 divided by 2. So the absolute value of I plus 1 divided by 2, I don't know why I wrote that again. So the absolute value of 1 plus I, in other words, the magnitude of 1 plus I, is equal to square root of 2 over 2, which is equal to 1 over square root of 2, which is less than 1. And just to remind you why the magnitude of 1 plus I is square root of 2 is because here I've plotted 1 plus I, right? 1 in the real direction, 1 in the I direction, imaginary direction. So the magnitude, the distance from 0 is going to be square root of 1 plus, square root of 1 squared plus 1 squared, which will give us our square root of 2. And since 1 over square root of 2 is less than 1, that means this series is convergent. For our second example, which looks a little complicated, so first I'm going to substitute n plus 1 into this expression. So I have n plus 1 factorial squared, 3 minus I, and 2 to the n. So I'm going to go 2 to the n plus 1 over 2. And since this is 2 times n plus 1, that's 2n plus 2 factorial times, and then I'm just going to take the reciprocal of this, which is 2n factorial over n factorial squared, 3 minus I raised to the n, 2n, all in absolute values. Since n plus 1 factorial is equal to n plus 1 times n factorial, I kind of algebraically made this equal to n plus 1 squared times n factorial squared. Over here, I still have my 3 minus I raised to the 2n plus 2. And then my 2n plus 2 factorial, I made that equal to 2n plus 2, 2n plus 1 times 2n factorial. So now I can simplify with some elements over on this side. In particular, I can cancel my factorials and this factorial squared. And over here I have 3 minus I to the 2n, so I can cancel all but 2 factors of that. So now I'm going to be left with n plus 1 squared times 3 minus I squared all over 2n plus 2, 2n plus 1. I'm going to pull out my 3 minus I squared since it doesn't depend on n. And then on top, I'm going to have n squared plus 2n plus 1. On the bottom, I'm going to have 4n squared plus 6n plus 2. And remember, I had told you when you take the limit as n approaches infinity, you only need to look at the highest powers. They're equal. So you remember, if on top, if it's high, the power is higher than on bottom, then it's going to go to infinity. If the power on bottom is higher than on top, then it goes to 0. But here they're equal. The highest power is both 2 on top and bottom. So the limit will be the ratio of their coefficients. So that would be 1/4. And what I'm left with is the absolute value of 3 minus I squared from here. And then I have 1/4, right? The absolute value of 1/4 is just 1/4. Now the magnitude of 3 minus I squared, again, right, if you think of this, this is 3 and then minus I. So the magnitude of this is 3 squared plus 1 squared. So that's going to give me my 9 plus 1 square rooted, and then I square that. So it's the magnitude, which is the square root, squared times 1/4. So that's going to give me 5/2, which is larger than 1. So again, this is our example where it diverges. And now we're up to our last topic, where we introduce the Taylor and Laurent series of real numbers. And actually, yeah, we're going to do of real numbers. So the Taylor series expansion we had talked about before. So it allows us to approximate any function with a polynomial. And the formula looks like this with the C of n formula given here. And we can talk about whether or not the Taylor series converges if the limit as n approaches infinity, and we look at this kind of ratio test here. So let's do an example of the Taylor series expansion. And actually, this is an example I have used previously in a previous video. Previously, when we did this, this series expansion, I used kind of a little bit different look for this formula, so we'll just use the formula that we're given in your book now. So we're going to approximate the f of x equals sine of x using a Taylor polynomial. And we're going to center our approximation at x naught equals 0. So this is where our approximation is going to be best. And in fact, it'll be exact at x equals 0. As we move further away, our approximation will get worse. But anyway, so we'll start with x at x equals 0. F of x, again, is our sine of x function. Now, according to our formula for C0, our first coefficient, C0 is equal to 1 over 0 factorial, which is equal to 1, in case you weren't aware. 0 factorial is equal to 1. Then the 0th derivative of f of x. And the 0th derivative is just f of x, evaluated at x equals x naught, so evaluated at x equals 0. So this is equal to f of 0, which is sine of 0, which is equal to 0. So again, our first approximation is the single point 0, which is extremely accurate when at our center, not so accurate everywhere else. Well, every now and then it's accurate, but it's basically accurate at one point. Continuing on, then C1, according to our formula, is going to be 1 over 1 factorial df1, the first derivative of f of x with respect to x, and then x evaluated at 0. So this is f prime at 0. So f, remember, is sine, so the derivative of sine is cosine, evaluated at 0 is equal to 1. So our next approximation, f of x, is going to be c naught, which is 0, plus c1 times x minus x naught, which is x minus 0. So we have 0 times 1 times x, which is equal to x, which is this line here. So now we're approximating our sine wave with this, this line, y equals x. So you can see near x equals 0, this approximation isn't bad. But as we move further away from x equals 0, our approximation isn't always so good. Calculating C2, we have 1 over 2 factorial f double prime of x evaluated at x equals 0, which is 1 over 2 factorial f double prime evaluated at 0. So that's 1 over 2 factorial. So the derivative, the second derivative is sine, the first derivative is cosine, so the second derivative is negative sine, evaluated at 0 is simply 0. So that, our next term over here is 0 times x minus 0 squared. So the x squared term has a 0 coefficient, so I'm not going to add that on for now. I will add one more term. So C3, now we have 1 over 3 factorial f to the third derivative evaluated x equals 0. So 1 over 3 factorial f3 evaluated 0 is 1 over 3 factorial minus cosine evaluated 0 is minus 1 over 3 factorial. And what you see now, what we have for f of x, we have c0 plus c1 x minus 0 to the first power minus c2 x minus 0 to the second power plus c3 x minus 0 to the third power. So c0 was equal to, where is it, 0? c1 was equal to 1 times x. c2 is equal to 0, but c3 is 1 over 3 factorial. So this is now our approximation for the sine series. So what you see is this green. Now we're approximating our sine series with this cubic kind of expression. And you notice how C2 was the coefficient for the quadratic expression. There was no quadratic expression as part of our sine, because the quadratic would have been something like this, which doesn't really model it. So the quadratic has no place in here, which is why this part is 0, just kind of a side note. So the idea is as we add more terms, we'll get closer and closer to this sine wave. I have a new Taylor series expansion example to show you, and this is one I probably should put on our overview slide, but to be quite honest, I didn't have room. And this one, this formula will become, or our Taylor series expansion will become important later. So it's one worth remembering, like jot it down somewhere. It's also noted in your book. So let's expand this function using a Taylor series expansion. So f of x is equal to 1 over 1 minus z, and we're only concerned with z less than 1, so we don't have a problem of it not being analytic. And I'm going to expand around x equals 0, which kind of makes sense. It's kind of the center of this interval as well. So f of x, which is 1 over 1 minus z, evaluated at 0 is equal to, well, at 0 here we just get 1. And then I can plug in to our formula for our coefficient, so 1 over 0 factorial, remember that's equal to 1, times the derivative, the 0th derivative, another f of x evaluated at x naught, is equal to 1. So c1 is equal to 1. To do my first derivative, I'm just going to write 1 minus z, or 1 over 1 minus z as 1 minus z to the negative 1. So when I take the derivative, I'm going to have the negative 1 come in front, and then 1 minus z to the minus 2, so that's this, and then derivative of what's inside, so I get another negative sign, so that becomes positive. So this is my second derivative, evaluated at 0, again plugging in a 0 into z, I get 1. Now c1 now is equal to 1 over 1 factorial, which is just 1. The first derivative with respect to x, evaluated at x naught, evaluated at 0. The first derivative is just equal to 1, so my c1 is equal to 1. Again, I'm going to write my f prime of x, the 1 over 1 minus z squared, as 1 minus z to the negative 2, so I can easily take my next derivative. So I have a negative 2, which when I multiply by the derivative of what's inside, the negatives cancel, so I'm going to have a positive 2, the 1 minus z to the negative 3. And evaluating the second derivative at x equals 0, then I'm going to get 0 here, so I'm going to get 2 over 1, which is 2. And my c2 then coefficient is going to be 1 over n factorial, in this case n is 2, so 1 over 2 factorial times my derivative, second derivative evaluated at x naught. So the second derivative evaluated at x naught is 2. So here the 2 factorial cancels with this 2, and I'm left with 1. I'm going to rewrite this as 2 times 1 minus z to the negative 3. So when I take the derivative, I'm going to get the negative 3 times 2, and then because the derivative of what's inside is negative, that'll cancel my negative, over 1 minus z to the 4th. When I evaluate this at 0, I get 3 times 2, and I wrote it this way because my c3 my third coefficient then is 1 over n factorial, which is 1 over 3 factorial, times, and then 3 times 2, that's also 3 times 2 times 1. So that's times 3 factorial. These factorials cancel, and I get 1. You can kind of see the pattern here. By the time I take the derivative, the 4 will come down, in which case I'll have 4 factorial, and then my Cn is going to be 4 factorial. So I'm going to keep getting coefficients of 1, which means that my 1 over 1 minus z is equal to 1 plus my first coefficient 1, x minus 0, plus 1 times x minus, remember x naught is 0, so 0 squared, plus 1 times x minus 0 cubed. So I get 1 plus x squared plus x third. So I have the summation of z to the n. So this formula here is what we'll be using this later, but I'll also remind you of this formula when the time comes. Oh, and I should also say, in this interval where z is less than 1, this series converges absolutely. Next, we're ready to talk about the Laurent series expansion, which we will use extensively when we talk about the residue theorem. So this is something you want to get. And the Laurent series expansion is essentially, and this is the formula for the Laurent series expansion. It estimates a function f of x with a kind of a polynomial here, just like the Taylor series. And in fact, this part is the Taylor series. So the Laurent series expansion is kind of an extension of the Taylor series. It also adds now negative exponents of x minus x naught. And this negative part, these negative exponents, this part of the Laurent series expansion is often called the principal part. This part over here with the positive exponents on the x minus x naught, that's called the analytic part because it's always analytic. So again, it's an extension of the Taylor series expansion. And in this part of the book, or at this point, we do not have the formulas for these negative coefficients. We'll do that in a couple of videos later. So Laurent series convergence, we can perform 2 ratio tests, one for the positive terms and one for the negative terms. And clearly, if there are any terms with negative n values, in other words, over here, the series cannot converge at x equals x naught. So in other words, by the time you get to this principal part, you have you can't converge at x equals x naught because this principal part will not be defined since you have division by 0. So in general, a Laurent series will converge in a symmetric range of x given by this d minimum or delta minimum is less than x minus x naught, which is less than delta max. In other words, there's this symmetric range and where it'll converge, but only around a small area around x naught, where d min and d max are the minimum and maximum allowed distance from the expansion point x naught. So we've talked about Laurent series convergence, but we don't really have the formula for this principal part. That said, I do have this one example for you, and it's kind of a trick question, but it was in one of my books, so I pulled it out for you here. So find the Laurent series expansion of f of z equals 1 over z minus I squared. And the trick is this function here is already in Laurent form, right? Because this here, this z minus I to the negative 2 power is exactly this term. It's a single term Laurent series. All the other coefficients are equal to 0, except for the c minus 2. And so z minus I squared in the numerator is already in Laurent form, where n, our Cn, is equal to negative 2, and x of x naught over here is equal to I. All the other values of Cn, except for n equals negative 2, are equal to 0. To summarize what we have covered in this video, we started to introduce the Taylor and Laurent series. First, we talked about convergence of a real series. So we said that a real series will converge to a value of s if they converge to a finite real number. The sum is equal to a finite real number as n approaches infinity. Absolute convergence was if the absolute value, the sum of the absolute values of x of n converges to a finite real number. And we can use the ratio test to establish absolute convergence here. And that is, if we take the limit as n approaches infinity of the absolute value of x of n plus 1 over x of n, and it's less than 1, then the series converges absolutely. Next, we talked about convergence of complex series, which was very similar to the real series. So an infinite summation of complex numbers Zn is said to converge to the complex value s if s is equal to the series from n equals 0 to infinity z sub n approaches a finite complex number. For convergence of an infinite complex series, the real and imaginary parts must converge. And what we used, though, to prove convergence was the ratio test, and it proved absolute convergence, sort of like absolute convergence up here. A complex series converges absolutely if the sum of the absolute values of the Zn approaches a finite complex number, and we have this ratio test to determine if an absolute series converges. It converges at the limit of n as n approaches infinity of the absolute value of z sub n plus 1 over z sub n is less than 1. And we did several examples. Next, we talked about Taylor and Laurent series of real numbers. We reviewed the Taylor series expansion given to us by this formula, and we did the example with sine. And we saw as we added more terms, we got a better and better approximation of sine. And then finally, we talked about the Laurent series expansion, which is an extension of the Taylor series expansion, because you can see the positive exponents here, where our exponent of x minus x naught is positive. That's actually the Taylor series. And then how the Laurent series extends the Taylor series is now it allows for negative exponents of our x minus x naught term. And we haven't discussed how to find the coefficients of these negative exponents, because that's for probably the next video, or maybe 2 videos later. Okay, so that was our introduction to Taylor and Laurent series. So that's it for this video. Thank you for watching.